Hello friends, welcome to Crackgate CSE, and in this series of algorithm today we will be understanding matrix chain multiplication. So this is also one of the application of dynamic programming approach. So before starting this video, I would like to request you all, if you have not subscribed to the channel till now, please subscribe the channel and press the bell icon so that you can get an update whenever I am uploading any new video. So now let's start with the matrix chain multiplication. So before matrix chain multiplication, there are some basics required to understand this. First of all, we'll see how matrix multiplication work. Then we'll see that what is the requirement of matrix chain multiplication and what is the actual goal that we have to achieve using this particular application, right? So for matrix multiplication, let A and B are two matrices. So I am having A matrices with number of rows as 2 and number of columns as 3. So these are the dimensions of matrix A, and these are the dimensions of matrix B, that is 3 to 4. So you already know that the number of column in A has to be equal to the number of rows in B. If this condition is satisfied, it is known as matrix compatibility. So if the two matrices are multiplication compatible, then only we can multiply. So there is A matrix which is having 2 row and 3 column. So let's say this is matrix A which is having the dimensions as 2 by 3, that means 2 rows and 3 columns. Similarly, let B is a matrix with 3 rows and 4 columns, right? So I am having 3 rows and 4 columns, so this is of 3 by 4. So here you can see that the number of columns, that is this 3, is equal to the number of rows of this B, that means this 3 is same. If this is the case, then only we can multiply it. Now if you multiply it, you can see that all of these 3 values will be multiplied with all of these 3 values to give one element. What does it mean? That means, let's say if the result is stored in C, if C is equals to A into B, and then C will be having 2 rows and 4 columns, right? So it will be having 2 rows and 4 columns. So the dimension for the output will be 2 by 4. For this particular one value of C, this complete row gets multiplied with this complete column. So how many multiplications are there? See, the first element will be multiplied with first, then second will be multiplied with second, and third will be multiplied with third. To get one element, we have to do 3 multiplications. Similarly, for the second element, I have to do 3 multiplication. So can I say that for 2 by 4 element, I have to do 2 by 4 by 3 multiplications, right? So I can write it as, you can see that this is 2, this 3, this is 4. So I can also write it as 2 is to 3 is to 4. So we'll be using this thing throughout the application, throughout this matrix chain multiplication. Now one important thing is that we know that matrix multiplication is associative. Associative means it doesn't matter in which order you are multiplying, but the result will be same. For example, there are 3 matrices A, B and C. So if you multiply AB first, then you multiply with C, that will be equivalent to A multiplied with BC. The output in both of the cases are same. So if the output is same, what is the use of matrix chain multiplication? So here you can say, here our motive is not to get the result. Here our motive is to get the minimum number of operations, that among this or this, among these 2 approaches, which approach is efficient, right? Because the number of operations in this particular approach cannot be equal to the number of operation in this particular approach. They may be equal, but at most of the time the number of operations vary at very huge amount. So let's see, I am having A, B, C 3 matrices with dimensions as given below. So these are matrix multiplication compatible because these values are same. That means number of columns is equals to the number of rows of the matrix. So there are two approaches in which we can multiply. So one approach is that I multiply a b, then I multiply with c. If I am using this particular approach, first I need to multiply a with a and b. So to multiply a with b, I need 10 into 30 into 5 multiplication. That is 10 into 30 into 5 multiplication, just as I explained you here, right? So this much multiplication is required to get what? AB. Now the AB dimensions will be 10 into 5. The output will be 10 into 5. We already know that. Now the C dimension is 5 into 60. Now I have to multiply this AB matrix. This AB will be treated as a complete matrix because we have multiplied it. So this AB matrix will be multiplied with C. And if I multiply this AB matrix, which is having dimension as 10 into 5, and here we are having dimensions 5 into 16, that means they are matrix multiplication compatible. The number of matrix multiplication required will be 10 into 5 into 60. 10 into 5, this 5 is common, into 60. So this much multiplication is required to find out the output using this particular approach. So what will be the value? It will be 1500 plus what it will be? 3000, right? I think yes, I wrote the same. Yeah. So it will be 18,000. Sorry, 1800. It will be 1800. But if I use this particular approach, that is A is multiplied with BC. So first I have to get rid of this BC because BC is in parenthesis. So this priority. So if I multiply this BC, how many number of multiplications required? 30 into 5 into 60. So 30 into 5 into 60 required for BC. Then this BC will be of dimensions 30 into 60. Now I have to multiply this A with BC. So A is having dimensions as 10 into 30. So if I multiply this is matrix multiplication compatible. So it will be 10 into 30 plus 60 operations. So completely we know we need to compute this much time multiplication to get the value. So what it will be? It will be 18,000 plus 9,000, right? So this will be 27,000, right? This will be for, sorry, I wrote it wrong here. So it will be 4,500, right? So here you can see that in this second approach I need to multiply 27,000 times, but here I need to multiply 4,500 times. So you can clearly see that this first approach is far better than this particular second approach. So our objective in matrix chain multiplication is to find a way in which minimum number of multiplications are required, because if we have to compute the minimum number of multiplications, then only we will be having the efficient result in less time. So what is our objective? Our objective is to find the minimum number of applications, right? So now see this particular example. So now we will be using a tree approach to solve these kind of questions. So the matrix multiplication problem can come in your GATE, UGC NET and any other competitive exam. So if you try it solving using the tabular method, it might be quite tricky for you. So I am telling you an approach which is the tree approach. This is very simple approach, and if you practice 2 to 3 questions, you will be fluent with this approach. So I have to multiply A, B, C, right? There are 3 matrices given with the dimension. So what are the 2 different approaches? That means whether I apply A with BC or I apply AB with C. So these both will give you same output. Now the question is, how many minimum number of multiplications are required? So here BC. First of all, I need to get rid of this BC. So BC will require 5 into 3 into 4, right? So 5 into 3 into 4. So this much multiplication is required for BC. Then BC will be of dimension 5 into 4, right? So what is it? It will be 60. Now I am having A dimension as 2 into 5. So these are same, that means they are compatible. So now I have to combinedly check what is the multiplication required for this. So it will be 2 into 5 into 4. So this will be equal to 40. So what is the total number of multiplications required? That means 40 plus 60, 100 multiplications required using this approach. Now check for this. If I go with AB, for AB I need to do 2 into 5 into 3, then AB will be of 2 by 3. 3 is already given as 3 by 4. So if I check it combinedly, it will be 2 into 3 by 4. So it will be 30. It will be 24. So now if you add these two, you will be getting as 54. So you can clearly see that minimum number of multiplication required to multiply ABC is 54. So the answer will be 54. So this way you can solve the questions. Now let's solve one question in which I am having 4 matrices. Then the tree will be a bit different. Now let's see this. So here I am having these 4 matrices and I have to find out what is the minimum number of multiplications required if I multiply all of these together. So here you can see that I am having A, B, C, D. So what are the different approaches we can use? That I am taking A separately and multiplying B, C, D together. Next approach is I am multiplying AB, then multiplying CD. Next approach is I am multiplying A, B, C together and D after that. Now if you expand this tree, this BCD can be multiplied in 2 ways. I explained you earlier that B with CD or BC with D. Similarly, I expanded this particular ABC. So now we have to start from the bottom. We have to use the bottom top approach. So we will be starting solving the questions from the bottom and then we will be heading towards the top. So first of all, I am taking for this BCD. Here I need to find out first for CD. So for CD I will be requiring 3 into 2 into 4 because this is compatible. So 3 into 2 into 4 is equal to how much? 24. Now the CD became by 3 by 4. So the dimension for CD is 3 by 4. Now I have to multiply it with B. So B is having dimension is 4, 3. So this 3 and 3 is same. I can multiply. So if I multiply this, this will be 4 into 3 into 4. So what it will be? It will be 48, right? So if I add this, this is 24 and combinedly this is 48. So I need to add 48 with 24. How much? 72. So 72 is for this BCD. Now check for this right hand side. Here if you check for the BC first. So BC is 4 into 3 into 2. So 4 into 3 into 2 and the BC is became 4 into 2. So the dimension for BC will be 4 into 2, right? This will be nothing but 24. So for BC I am getting 24. Now the dimension of D is 2 by 4. Now I have to combinedly multiply. Then what it will be? It will be 4 into 2 into 4. Because of this, so what it will be? 32. So if you add this 32 with this 24, you will be getting 56. So among these two, we have to select the minimum. So minimum is 56. So I selected 56 for this BCD. Now the dimension for the BCD will be 4 by 4. You can check from here also. You can check from here also. So it will be 4 by 4. Now what is the dimension of A? 2 by 4. So now you have to multiply combinedly. So for this it will be 2 into 4 into 4. 2 into 4 into 4. This will be nothing but 32. Now add this 32 with this 56. So it will be 88. So 88 for this kind of approach. So 88 for this kind of approach. Now go with this second approach for AB. Now for AB, if you check, we will be requiring 2 into 4 into 3, and the dimension will be 2, 3 for AB. Similarly, if you check for CD, it will be 3 into 2 into 4, and dimension for CD will be 3 into 4. So it will be 24. It will be 24, right? So 24 for this AB, 24 for this CD. Now I have to combinedly multiply this AB with this CD. So if I multiply it combinedly, what is the dimension? 2 by 3 and 3 by 4. So it will be 2 by 3 by 4. It will be again 24. So if I combinedly multiply it, 24. So 24. Now add these 24, 24, 24. It will be 72, right? So now this is somewhat better approach than 88. Now let's check for the third case also. So for third case, if you check that, I already solved AB, which is giving me 24 value, and the AB was of dimension 2 into 3, right? Now check with C. C is having dimension as 3 into 2, and if you solve it, it will be giving you 2 into 3 into 2, 3 to the 6 to the 12, right? So how much it will be giving? I think everything is right. I haven't did any mistake, right? So 2 into 3, AB is of 2 into 3, right? C is of 3 into 2, right? So combinedly 2 into 3 into 2, right? So 3 to the 6 to the 12. So now sum 24 plus 12 will be 36, right? Now check for this. So we did BC earlier also. For BC I am getting as 24, and the dimensions we are getting as 4 by 2. Now multiply this with A. A dimension is 2 by 4. So combinedly it will be 2 by 4 by 2. So it will be 16. So combine this 24 with this 16. So if I combine this 24 with 16, it will be 40. Among these two, 36 is better approach. So we have selected this approach. Now ABC will be of 2 by 2. You can check from any of these two. So this will be of 2 by 2, and D is of 2 by 4. So if I multiply them combinedly, it will give me 2 by 2 by 4. That means it will give me 16. And if I sum this 16 with this 36, it will be 6, 6, 2 and 52. So now you can see that among these three approaches, this 52 is giving me the better option as the minimum number of multiplications. What will be the answer? 52 will be the right answer. Now here you can see one thing, that here I am using the dynamic approach. Why? Because every time we are taking care of all the possibilities. We are not leaving any possibilities. So if we are taking care of all the possibilities, it is nothing but dynamic program, because in greedy we do not cover all the possibilities. We try to cover only those possibilities which can be solved in minimum amount of time, because of which greedy does not give always the correct answer. But here we got the correct answer as 52. Now let's see what will be the recurrence relation of this particular application. So MCM, matrix chain multiplications, I am renaming the function as MCM I comma j, where I is the starting matrix and j is the last word matrix. So here you can see that I am having n is equal to 4, because 4 matrix is to be multiplied. So from starting from 1 I will go up to 4, right? This is the meaning of MCM I comma j. Now if I is equals to j, that means if there somewhere it is MCM 1 comma 1, that means if there is only a, nothing else is around with this, then we can simply return 0 for this particular value, right? This is what this first condition says. Now if I have to multiply, you can see that here I got the 3 subtree, and for each subtree I calculated some values using the expansion or the recursive method. Then I selected the minimum values out of these 3. So same here also, I am selecting the minimum from the 3 different subtree. Here we are multiplying A with BCD, that means this is 1 to 1, BCD means 2, 3, 4, that means 2 to 4. So this is what I written over here. MCM A alone, that means 1 comma 1, BCD, that means 2 to 4. So this is a series from 2 to 4, chain from 2 to 4. Now once I got some values for this, some values for this, you can see that for A I am having these values 2 comma 4. So let me write down here. For A the dimension was 2 comma 4. For B, C, D I got the dimension as 4 comma 4 after solving. Now this P0, P1, P4 is, when you multiply them together, this P1 is equal to 2, this 2, sorry, this P0 is equal to 2, this P2 indicates the value 4, and this P4 indicates the value this one, right? So this is P0, this is P1, sorry. So this is P0, this is P1, this is P4. So if you multiply it together, what we was writing here is, we was writing 2 into 4 into 4. See, this is what I written here, 2 into 4 into 4. So similarly 2 is equal to P0, so I am writing P0. 4 is equals to P1, so I am writing P1. This 4 is equal to P4, so I am writing P4. This is nothing but multiplying these two sub matrices, right? And then we'll be adding the number of multiplications we got for this, the number of multiplications we got for this. Similarly we are checking out for this particular case where I took AB together and CD together, that means 1 to 2 in one chain and 3 and 4 in one chain. So 1 to 2 in one chain, 3 to 4 in one chain. Similarly if I am doing this stuff, you can see one thing here is that here we find out AB first. So for AB I got 2 comma 3. So for AB, where I should write C, for AB I got 2 comma 3, for CD I got 3 comma 4. So here the P0 is equals to 2, this particular value, P2 is equals to this 3, and P4 is equal to this 4. So when we are multiplying this, I will be multiplying P0 with P2 with P4. So this is what is written here. Similarly I am expanding this third one. So how to write it in a general form? So if I try to write it in a general form, I can write it as MCM of I comma j is equals to 0 if I is equals to j, this is same, then minimum of MCM I comma k. I is the starting value, k will be any value which is lying between j. You can see that k is the value which is lying from 1 to 4 in this particular question. So k is varying for the first loop, second loop, third loop. You can use it as a loop when you try to write on the program. Now similarly MCM, in any place you can see that this is 1, this is 2, this is 2, this is 3, this is 3, this is 4. So I can write this is k, this will be k plus 1 comma j. I can write it like this. Then I am adding these stuff, right? So this will be nothing but this I, so pi and multiply with this is k, so p k multiply with p j. So this will be calculated for all the value of k. So there will be some such sequences. So I am writing out the general formula only. This will be the recurrence relation if I is equal to j, otherwise. So you got the recurrence relation. Now let's try to find out the time complexes. So I am not showing you the complete algorithm over here because I think that you can easily manage by this particular recurrence relation. And in case if you are getting any problem with understanding the code, you can easily find it out on Google. Just type on the Google the code for matrix and multiplication, you will be getting it. You can run by taking some values, you will be easily getting how you can do that. So this is the recurrence relation. Although the program or the algorithm will not be asked in a gate question or in any competitive exam, so I'm not explaining you it here. They only give you the questions like this. They will give you some matrix and they will be asking you what is the minimum number of multiplication, or they can ask some question on the basis of this recurrence relation. So do not worry about the algorithm. Now let's see what is the time complexity. So if you check here, if you check at this particular page, here I am taking the tree method. So how many levels we are having here? So here I am having 4 matrices, so the level will be 4, because this CD can also expand it, this BC can also expand it. So overall we will be getting 4 level, first level, second level, third level, and this fourth level, right? So if there are n level, and you can see that this is not a binary tree, this is not a binary tree. So let me just take a fresh paper and let's try to understand over here. So if I am finding out the MCM of 1 comma n, then what I will be getting? I will be getting n level tree, that to which tree? N array tree. Unlike the previous applications like knapsack, LCS, we was getting the n level binary tree. That's why the time complexity was different. But here you can see that I am getting n level tree, that too of n array. So if I want to find out the number of nodes, how we can find out? For n level n array tree, the number of nodes will be equals to n to the power n minus 1. This is a formula. So this much nodes will be there. And for each node is related to a function call. Each node can be treated as a function call, and each function call, let's say, so this is n to the power n, and each function call will be taking n time to solve, because here we are talking about the multiplication. So if I need to perform the multiplication 3 times over here for 3 matrices, that means we are taking n time. So I can write it as order of n to the power n plus 1, right? So this will be the time complexity without using the dynamic programming, because we are not using any table concept as of now. We are trying to execute, we are trying to compute all the functions. Here we have executed all the functions one by one, right? In that case, the time complexity will be equal to order of n to the power n plus 1 without dynamic programming, right? Now let's check for the space complexity. Space will be nothing but input plus extra. So input will be, I am taking 4 matrices, so I can take 4n. Extra will be n byte, because of the tree we need n level we need n stack space. So the space needed is order of n. Now you can see one important thing over here is that so many functions call are repeating, and if functions call are repeating, let's see, this AB is repeating here, this BC is repeating here, this CD is repeating here. Similarly, so many functions call are repeating. So if there is any function call which are repeating, it gives you a hint that you can use the dynamic programming concept. And if we can use the dynamic programming concept, the first question will be how many distinct function call we need to execute, because the time complexity always depends on the number of distinct function call that is to be executed. So the next question is how many function call, that two distinct, how many distinct function call are there in matrix chain multiplication. So if the matrix chain multiplication is of size n, so how I will be expanding? I will be checking 1 with n also. If I talk about 1 comma 4, so if it is n value is 4, then I will be checking 1 both 4 3 2 1 all the possibilities. Similarly 2 with 3, 2 with 4, 2 with 3, 2 with 2, 2 with 1. Similarly with 3 with all these values and 4 with all these values. So can I say that there are n way for this and there are n way for this? So combinedly it will take n into n discrete functions call. That means n square discrete function call. And I already told you that each function call will take order of n time because of the multiplication. Right, I told you here. So if there are n square function call and each function call is taking n amount of time to solve it, to compute it, then I can tell that the time complexity will be nothing but order of n cube, because we will be storing the function once, then we'll be computing the function once, and then we'll be storing its value in a table for the later reference. So in this way we have to compute a function only once. That's why we are finding out the distinct function call. So the time complexity using the dynamic programming is order of n cube using dynamic programming. Now let's check for the space. Space is nothing but input plus extra. Input is already n because we are taking n value, so this is n, here also it is n. In extra we are taking two things, stake plus in dynamic programming we use some table to store the values. So stake will be n because of the n level, but table we need to have of n by n size because of this. So if I need the table to be of n by n size, n square, then that will dominate the space complexity. So we can say that the space complexity is order of n square. So here you can see that the time complexity has been decreased and the space complexity has been increased. So if you try to decrease the time, it will take more space. If you try to decrease the space, it will take more time. So this is how you can find out the time complexity and solve the questions on matrix chain multiplication. In the next video I will be talking about few previous year gate questions on matrix chain multiplication. So these are the important questions. Don't forget to watch that video. I'll be hopefully uploading it tomorrow, right? So if you found this particular video useful, like this video, share it with your friends, and don't forget to subscribe the channel if you have not subscribed till now. And if you really appreciate my effort, please like the video and don't forget to mention your comments, because your likes and comments are like motivation. So I always get motivated when I see your comments and likes to work more hard for you. So thank you very much for your support. And in case if you are having any query, any doubt, you can post your query on my Facebook group or Facebook page. Link is given in the description. So thank you very much for watching. Keep watching, keep loving, keep supporting, keep learning. Have a great day.